Hello, everyone, and welcome to another episode of Physics Chat, a show where we delve into the life and research of physicists at the forefront of their fields. In today's episode, we're joined by the friendly faces of Sergi and Joe. How are you both doing?
Very good, thank you. How are you?
Yeah, good, thank you. We have a special guest today. We're joined by Dr. Laura Nuttall, who is one of the faculty members here at the Institute of Cosmology and Gravitation. Laura's research focuses on the detection of gravitational waves. Thank you very much for coming on the show, Laura. How has your bank holiday weekend been?
Thanks very much for having me, everyone. It's been a lovely bank holiday, actually. Me and my son went to the park, I think, every day.
Nice. Yeah, it's been great weather. So we've heard about gravitational waves before in some previous videos that we've had on the channel, but could you quickly summarize for us what gravitational waves are and delve a little bit more into some detail about how we measure them?
Yeah, sure. So gravitational waves are called ripples in the fabric of space-time, and they travel at the speed of light. And this can be a bit of a really strange and alien concept for folks because most people don't deal with space-time. So the way to think about space-time is kind of like a four-dimensional trampoline. 4 dimensions, it's the X, Y, Z kind of coordinates, so like your position plus time, and you have to couple all of those together to actually understand what space-time is. Now, I can't think in 4 dimensions. Much easier to think of about just a regular old trampoline that you might have in your back garden. I'm getting towards here what the idea of gravity is in this picture of the trampoline. You have to think about what Einstein says about gravity. And what he says is that gravity is simply the curvature of space-time. And so I've got my trampoline that is space-time, for instance. Let's say I put a ball on this trampoline. The space-time will bend ever so slightly around the ball. I remove the ball, let's say I stand on it or something like that. I have much more mass than the ball, and I will cause the trampoline to bend even more around me. And it's the bending of space-time, this curvature, that dictates how strong gravity actually is. And so anything will cause a bending in space-time. Me, you, the Earth, the sun, I can go even bigger and bigger and bigger. And so bigger, more massive objects will cause space-time to bend more around them, will have more gravity associated to them. But in the same way that a boat moves through water, or an object moves through space-time, they'll cause ripples in the fabric of space-time, or in this case of a boat moving through water, they'll cause ripples in the water. And it's these ripples are what gravitational waves actually are. And so really you might be coming to the conclusion that there's a lot of things that are going to produce gravitational waves, and you'd be absolutely right. Me waving into the screen right now is actually producing gravitational waves into the screen. They're just really, really weak, and you can't really detect them. They're very different from, say, electromagnetic waves like light or X-rays or microwaves. Pretty much anything produces gravitational waves, but kind of the sources that I go after, colliding black holes and neutron stars, will produce some of the most detectable sources of gravitational waves that we'll be seeing here on Earth. And so the way that I detect these types of signals is with a massive microphone that's called LIGO, the Laser Interferometer Gravitational Wave Observatory. And so it's very different to a conventional telescope where you don't simply point at a light source in the sky or something like that and go, oh, that's pretty, that's changing. I have absolutely no idea when gravitational waves are going to be coming by, so I just have to listen for them all the time. And so with my detector, I'm trying to, if you like, hear black holes colliding. Gravitational waves are really quite nice in that they have a stretching and squeezing kind of effect on things. So if they came in or out of the screen right now, what would happen is they would cause me to potentially like expand this direction and get a little bit shorter, and then half the wave cycle through would make me be a little bit taller and a little bit thinner. And so you've kind of got this kind of like pulse stretching and squeezing idea that gravitational waves will actually have. And so my microphones are actually massive L-shaped interferometers. And so with my interferometers, I'm going to be trying to see the stretching and squeezing that gravitational waves are going to be having as they move through my instrument. And so if I set up my arms to be the same length, what actually happens is when my light reappears, it's constructively interfering because nothing's happened. The light has traveled the same distance and we've got back to the same portion here. But if a gravitational wave happens to come by and say, squeeze this arm or stretch this arm, the light might look a little bit different. It might have interfered. You might see patterns of constructive and destructive interference. I'm actually looking for a phase shift of the light. And how that phase shift appears will give me, if you like, a fingerprint of what gravitational wave came through and what sources actually produced them. So a nice way to think about it is 2 lines of soldiers march from the laser source and they march to the beam splitter. 1 line of soldiers up this arm, 1 line of soldiers up this arm. They each travel to the mirrors at the very end of the arms. My LIGO arms happen to be 4 kilometers long. very, very long. And so the row soldiers here marches 4 kilometers that way and 4 kilometers back. And so if I set up my arms the same way, each line of soldiers have both marched 8 kilometers. And when they reappear, they're still marching perfectly in time. Gravitational wave comes by, however, this arm may be slightly smaller, this arm may be slightly longer due to the passage of the gravitational waves. And so the soldiers will each have marched slightly different distances up and down at the arms. And so when they meet again at the beam splitter, then they'll be marching slightly out of time with each other. And that's exactly what we're looking for. We're measuring how out of time the phase shift of the laser light. And like I said, that'll tell us what gravitational wave happened to have gone through.
Fantastic. Thank you so much, Laura, for a really comprehensive answer and really clearing things up, I think, for a lot of us. You kind of mentioned that, for one, gravitational waves, at least for most things, are quite weak. Is that what makes them very difficult to detect? What else is going on that makes them quite hard to find in the first place?
Yeah, so gravitational waves are really weakly interacting with matter. So they're passing through us all the time and we're just not noticing. I quite often get asked by people like, what's the effect of a gravitational wave? Why can't I kind of feel it? And that's because gravitational waves will jostle the tiniest atoms in your body by the utter tiniest amount. My LIGO arms happen to be 4 kilometers long, and if I try to measure a gravitational wave coming through that, it'll actually change the length of one arm by something like 10 to the minus 18 meters. That's a crazy, crazy tiny amount. The size of an atom in your body is about 10 to the minus 15 meters, and 1,000 times smaller than that are my gravitational waves from black holes that are jostling your body. So that's why you're not really feeling anything.
I'm sure you'll have many fun stories of how we detect gravitational waves. Could you tell us some?
Yeah, so I used to love going to the detectors. One of the LIGO sites in Hanford, Washington, I visited multiple occasions. I think one of my favorites actually is a time when I actually wasn't at any of the detectors. It was actually the very first detection of gravitational waves back in September 2015. So we're at the point where we're ready to start the observing run. We're ready to turn everything on and go like, right, we're ready to do science now. Let's see if we can hear gravitational waves. But in preparation to do that, what we do is a number of tests to make sure that we can understand what is a real gravitational wave and what, say, is terrestrial noise. Because my detectors are crazy, right? They're trying to detect a length change of 10 to the minus 18 meters. There's so many things that make the detectors move by more than 10 to minus 18 meters. Trucks on the road next to the detector, for instance. Even me going for a run up and down one of the arms, not both of them, oddly enough, will cause noise that will make the optics jostle by more than that amount. So we need to understand if there's something that we do in the control room, could it actually affect us? Some of my colleagues have a very fun job of doing what we call physical environment monitoring injections. And so what they do are things like blast loud music in the control room and see if we can see it in the detector. Another time I've been in the detector control room actually, and I've just had a colleague go, right, everybody stand up. And then it goes 1, 2, 3, and jump. Thank you. And he's seeing if we can, people jumping up and down in the control room might couple to the detector, for instance. So they're doing all these weird and wonderful fancy things. So back in the 14th of September 2015, they were doing some of these random injections very early in the morning at both sites. I think it was something like 1 a.m. in Hanford, Washington, and 3 a.m. in Livingston, Louisiana. Can't remember exactly what they were doing, but they were trying to do almost simultaneous kind of things locally to the detector just to see what would happen to it. Now, luckily, my colleagues got tired at this point at 1 and 3 a.m. and decided it's time to go home. So this is just before the observing run. So what they do is when you leave for the night, you just leave the detector in observing mode. You just leave it and go, we'll see what happens. And off you trot and you go home. So they happen to be finishing their injections. And then about 20 minutes later, the very first detection of gravitational waves came through. So it's all serendipitous. It was super lucky that they decided that they were tired and they wanted to go home. And that signal happened to come through at that point. Blink and you miss a gravitational wave. This signal that came through a 36 solar mass and a 30 solar mass. So that's two black holes that are 36 and 30 times the size of the sun collided. That signal came through our detectors after 1.3 billion years of traveling through the universe. They went through our detectors in 0.2 seconds, and luckily 2 of my colleagues got tired and we detected them.
Yeah, so what's the status of gravitational waves now? Could you give us a current update of what we have discovered and what's next?
Yeah, so absolutely. So gravitational wave astronomy is still very much in its infancy. That's what makes it really, really exciting. So right now we're still at the point of discovery. As I mentioned, we've discovered about 90 objects colliding, producing more things. So we're starting to get a really good handle now of, 2 black holes colliding, creating larger black holes. We're getting an idea of the masses of the black holes that are being produced. We're getting a bit of an idea of the stars that died that then produce these black holes that then collide with other black holes, you know? So it's kind of like all backtracking and kind of understanding what things are going on. Other exciting things that have been going on is that typically if a neutron star merges with, say, another neutron star, potentially also a neutron star with a black hole, depending on the masses and things. Because there's matter involved in that system, they will also produce an electromagnetic signal. With the coupling of, say, a gravitational wave and an electromagnetic signal called multi-messenger astronomy, we're starting to understand more and more about, you know, where exotic matter, for instance, is made in our universe. So back in 2017, when we saw gravitational waves from two neutron stars colliding, hours later, folks happened to see the optical counterparts to that collision of these two neutron stars and happened to see things like platinum and other exotic materials being made in the system. So whilst we might be made of stardust, our rings and precious materials here on Earth are actually made of neutron star matter.
Real. And so are there any other types of gravitational wave detectors that are coming up?
Yeah, so it's going back to this idea of the gravitational wave spectrum. So LIGO, Virgo, CAGRA, they deal with the kind of hertz to kilohertz region. They're very much specifically looking for colliding black holes that are about the size of the sun up to, say, 100 times the size of the sun. If we go down the spectrum now to the millihertz, microhertz kind of region, there we're starting to probe even bigger black holes, thousands, hundreds and thousands, millions of times the size of the sun colliding with each other. So these might be, say, the black holes at the center of galaxies that are colliding with each other. There you need a different telescope than how LIGO works. You actually need to go into space to actually be able to hear these objects. And that's where the Laser Interferometer Space Antenna, or LISA for short, is going to open up that window of the gravitational wave spectrum. I think it's currently scheduled for mid-2030s to be launched. So by the end of the 2030s, hopefully we'll be starting to hear supermassive black holes colliding. There's other parts of the gravitational wave spectrum as well. The nanohertz region, that's where you've got the area of pulsar timing arrays that they're also trying to hear, like, if you like, the background of black holes colliding from everywhere in the universe. I bet they make a detection soon, so watch out for them, folks. And then if you go even further down into the gravitational wave spectrum, this is where you're looking for gravitational waves with really long wavelengths. And so there you're starting to look for gravitational waves from the very early universe. Gravitational waves are expected to be one of the only things that can probe the very early universe, such as inflation, and to understand what was going on at that period of time. And so there you might need something like a microwave detector or something like that to detect what we call B modes. I would certainly think over, let's say, the next 50 years, we should unlock the entire spectrum and understand what's going on.
That's super interesting. Thank you. I think we'll take a little break from the science quickly and segue into one of our random questions. We've heard that you're a big fan of musicals. And we were wondering that if you could be a character from any musical, who would you choose and why?
Oh, yeah. For somebody that is really quite tone deaf and is terrible at singing, I just love the idea of living in kind of like this land where people just randomly burst into song. There's so many musicals that I like, but I don't think I'd like to actually be in them. Like, I don't really fancy being, like, you know, in the Phantom of the Opera or something like that. That sounds quite, you know, scary and a bit. Ooh. So I think the funnest character that I can think of would be someone called Tracy Turnblad. I think it's she's called, in Hairspray. I love the idea of being back in the 60s, just for all of the, you know, just the get up and the garb and everything like that, the massive hair and just all of that music of that era. But I think also the story of Hairspray is really quite nice in terms of, like, just trying to get over the prejudices of the time, and very relevant obviously for today and things like that. And yeah, she just kind of really kicks ass and is just a really fun character. So I think I'd love to be Tracy out of Hairspray if I could.
So to get back to the physics, as you mentioned before, it's obviously quite challenging to take these projects from the initial concept to the launching into space. So after all this work, what are the aspects of your job that make it worth it in the end?
Oh, that's a really good question. I think there's a lot of aspects of my job that I really, really do enjoy. And I think some of the major ones are talking to people about it. You sometimes can forget just how cool your job is when you're doing it day to day. I think everybody can get bogged down in whatever it is that you're doing, or the politics of their job and stuff. But it's only really when you have a chat to someone on the bus or something and it's like, what do you do for a living? It's like, I try and detect black holes colliding. That's bloody cool. So, you know, it's just, I think those are the best bits of my job, being able to actually have a chat to people about it. I was talking to some A-level students yesterday about it, and they were coming up with all sorts of wonderful questions about anti-gravity and things like that to me that I had no idea about. I think that's the point. I don't know And that's fine, but I'm going to go and find it out. Physics just keeps you busy. It keeps you answering questions. And so, yeah, I think that's the nicest bit about my job.
That's cool. I really love hearing the positive outlook that you have on your career. And it sounds like there's a lot you've learned that has helped with that. Is there anything you maybe wish you'd learned a bit earlier or known earlier that would have helped things going on?
Yeah, if I could tell the younger Laura something, I think I'd probably be trying not worry too much about things. Like, things often have a way of working out. Like, people often think that I maybe had this grand plan that I'd be sat here, one day talking to you all about, finding and detecting black holes. And that really wasn't the case. Don't worry too much. There's some planning really involved. There's some strategy to, make sure that, you do good at your job so you can get the next one, or you go off and do this other thing. But yeah, probably try not worry too much. There's going to be interesting things. Kind of go with the flow a little bit, which is definitely not me at all.
Yeah, I think I'm a little bit of an over planner as well myself sometimes. So that's quite good advice, I think, and nice to hear. And I think that's all we have time for today. But it's been absolutely fantastic having you on the show today, Laura. Thank you so much for joining us. For those of you watching today, could you let us know in the comments if you're excited for the launch of our biggest space mission ever? And stay tuned for our final episode of season 3. It's been great to have you. Thank you all for watching, and goodbye.
Bye.
Bye.
Physics just keeps you busy. It keeps you answering questions.